Hi, my name is Gabriel Nuzzo, and I'm going to be walking you through my group's final design project, the Minnick wing. I worked with the following people shown on screen. I mainly worked on the FlexPD model, the model validation, and the final report. We are tasked with designing a combination piezoelectric-thermal resonant cantilever to act as an actuator for the new Minnick wing. Our goal is to maximize the transverse tip displacement of the cantilever when a 20 mV voltage source is applied across the metal contacts at the fixed end. The fixed end stays at a constant 25 degrees Celsius, which is the temperature of the surrounding environment. The outer faces of the device all experience heat transfer via convection with a convection coefficient of 20 watts per meter squared Kelvin. The actuator design consists of a quartz piezoelectric layer with a metal shell. First, we must determine whether to use copper, aluminum, or steel, and then we need to determine the ideal aspect ratio of the device and the ratio of metal on the top and bottom of the shell. Thermal strain is modeled as epsilon t is equal to alpha delta t, where alpha is the coefficient of thermal expansion and delta t is the temperature change of the system. It represents the strain caused by the increased kinetic energy of the particles through the addition of heat. Internal heat generation is caused by resistance to the electrical current flow in the materials. This is related to the current density and the electric field, described by Q dot vol is equal to J dot E. Piezoelectric strain is modeled by epsilon P is equal to D transpose E, where D is the piezoelectric coupling matrix and E is the electric field. Solving the piezoelectric strain for this material gives the following result. External sources of strain can be modeled with Hooke's law. In this problem, we assume that there are no external sources of strain and that the effects of gravity are negligible. Adding all of our sources of strain together, it gives us the total strain. Finally, the mechanical strain is related to the stress through the stiffness matrix C, which we solved for in Maple. The stress results in a displacement of the materials. We created two FlexPD models to solve the equations we discussed. Both models are in 2 dimensions and use the same geometries and material properties. In the beam resonance model, we set modes equal to 1, since we only care about the first mode. Here we model the relationships between stress and strain. Strain is determined by the relative change in displacement in each direction, and the stresses are modeled using Hooke's law. This equation represents the eigenvalue problem that we discussed in the theory section. Here lambda represents omega squared, which is what Flex will solve for in each mode. In our second model, we also define the piezoelectric and thermal relations that we just discussed. Here, FlexPD solves for the voltage difference through the device using the current density, which is related to the material's conductivity and electric field. The electric field is given by the negative gradient of voltage. We also define the internal heat generation from electrical resistance. By defining the boundary conditions on our device, Flex solves for the tip displacement, which we report. First, we tried running our resonant model with arbitrary values set for the geometry. The first mode of a cantilever should bend up or down from the anchor point in one direction with relatively constant curvature. This is confirmed by the FlexPD output. Next, we double the length and thickness of the device. We know that the resonant frequency is proportional to the height divided by the length squared. Therefore, we expect the resonant frequency to be half of what it was before, which is exactly what we find. Making the device twice as thick as it was in the original test should double the frequency. However, in FlexPD, we find it is somewhat less than this. This makes sense since when the device is not much longer than it is thick, shear effects start to become significant. This provides evidence for our resonant model's validity. In the tip displacement model, adding the voltage source with the thermal expansion coefficient set to 0, the beam bends down to piezoelectric strain as we expect. We can also see that the current flows from high voltage to low voltage, and that heat is generated in areas of high current flow as we expect. If we increase the voltage source by a factor of 10, the piezoelectric strain should increase by the same amount, causing the tip displacement to be 10 times higher than before, which it is. Now, adding in the thermal effects, we can see that the beam bends up. This is because more heat is generated in the thin piece of metal on the bottom, meaning it has higher thermal strain. In the final design, we'll set the voltage source so that both sources of strain cause bending in the same direction. All of our tests match theory, providing proof of our model's validity. Now we combine this FlexPD code with Python. In Python, we start by importing necessary libraries and initializing our FlexPD code as a string. We use %s here as a placeholder for the geometry parameters. Next, the getFlexValue function runs flex the given geometry and outputs the associated tip displacement. Then we use the optimum function to find the maximum tip displacement and the associated aspect ratio and metal ratio. We also graph our 2D grid search, which looks like this. Using the methods I described, our grid search method found a max tip displacement of 511.2 nanometers with an aspect ratio of 0.189 and a metal ratio of 0.778. Next, we completed a gradient descent optimization. The first part of the code is the same. Then the grad function finds the gradient of the objective function, which is the displacement in this case at a given point r. The gradient tells us the direction of steepest descent which we want to move towards. We use this to find a new value, and if it is better than the last value, we set this as our new optimum and continue searching. We do this 30 times. Using this method, we find a maximum tip displacement of 511.355 nanometers, which is within 0.2% of our previous result. This is associated with an aspect ratio of 0.188 and a metal ratio of 0.777. Finally, we use another script to find the best material. This script uses our flex model to find the tip displacement for our 3 materials at the high and low bounds of our search ranges. Taking the average of these results finds the average tip displacement of the device for each material. Then we output the name of the material with the highest average tip displacement. Putting this all together, we find the device has a maximum tip displacement of 511 nanometers and a resonant frequency of 16,280 Hz. This is associated with an aspect ratio of 0.19, a metal ratio of 0.78, and the best material is copper. This agrees with our theoretical predictions. We calculated our values to at least 3 significant digits, but we recognize that this is too precise to be accurate given the initial parameters and possible variances in material properties. We are confident to the level of precision of 2 significant digits for our ratios and dimensions. We validated this using FlexPD by varying the geometry by 1/10 of a millimeter, which produced accurate displacement. Our next step is to compare the resonant frequency to the time it takes for thermal effects to manifest to find a more accurate tip displacement. Thanks very much.